Um, that was a worrying message. So our little discussion got interrupted. I don't know how I'm going to stitch these together in post-production. So this week's video might start here. It looks like actually, Jackson, you're the only person in here right now. I mean, aside from me, myself, and I, in the sense that I also have the iPad. So doing this as a little bit as a lecture format feels a little bit awkward and impersonal if there's only one person around listening to me yammer on. So yeah, how do you feel? Have you've seen the fundamental theorem of calculus before? This like something you're familiar with? Do you want to go into a little bit more depth? Cool. But yeah, so we want to try and get a version of the fundamental theorem of calculus for multivariate calculus. And basically the reason we want this is because it'd be nice to have. I mean, in some sense, it's because the fundamental theorem of calculus really is what makes the derivative and the integral what they are. Like, the reason we really care as physicists what an integral is and what a derivative is kind of their relations. What lets us do things like, say, velocity is the derivative of position. Position is the integral of velocity. Like, the reason we can do all of those nice little conversions sort of rests pretty heavily inside the fundamental theorem of calculus. Otherwise, we wouldn't expect there to be sort of that easy hierarchy of position, momentum, acceleration, or position, velocity, acceleration, jerk. So yeah, last time we discussed the restriction of this to like 1D spaces, of multivariable function to 1D spaces a little bit. And it should be, I hope this is like obvious that if we restrict a multivariate function to a one-dimensional space, if we restrict it to like the y=0 line, now we just have a one-dimensional function. We can use the fundamental theorem of calculus. Because at that point we're back to the one-dimensional case. We don't need to do anything multivariable. Everything's nice and friendly. So we can actually start with this claim and sort of build outwards. We can start with the claim: the integral of any scalar function when restricted to an arbitrary parametric curve with respect to that curve's parameter has as its derivative the original function. And I should say the original function restricted to the parametric. But we can actually do better than that. So we want to improve this claim. And sort of how do we want to improve this claim? Ideally, we could somehow encode the derivatives of a scalar function with respect to any selected restriction. So ideally, we have this multivariate function, and we could work out what the derivative is sort of in any direction through some sort of process. We could sort of create some partner function. In the same way, the derivative is basically the partner function to the original function, whose integral is the original function up to a constant. Or vice versa, the indefinite integral of a function gives you a partner function whose derivative is the original function. We could produce some sort of partner function which contains enough information to sort of quickly and easily, ideally without doing any further calculus, pop out what the derivative is under sort of any restriction. And formally, what we're looking for is an operator, which basically means a thing which acts on other things. It's got a more technical definition, as you might imagine, but basically we're looking for something we can do to our function to produce this partner function. So we have O such that O of f gives us what we want, a sort of a full encoding of the derivative on arbitrary restriction. So we're going to look at how we do this. And we're going to look at how we do this on a whiteboard. So I'm going to start sharing as my iPad, creating a whiteboard. And basically, we have our function in however many dimensions as usual. And we're taking some arbitrary restriction right? So we've got that vertical sheaf. I love talking about these vertical sheafs. It's kind of just what I do. So we have that restriction, and we produce a new, monodimensional function as a result. As we've discussed before, and I keep on saying it, oh God, this is sort of ugly, but we keep on saying that I can cut, a curved shape using straight scissors. I keep on making this claim, right? So basically what I'm saying is that I've got my arbitrary restriction everywhere it's linear. We can go on to linearize if this is some C of, let's see, say T is our parameterizing function. We can go on to linearize our restriction by saying C sort of approximately around some time t naught is equal to C at t naught plus t times dc dt, defined at t naught. Right, so that's our linearization. And we've seen this expression for our linearization before, right? This is, the equivalent of saying f is approximately f at like some x naught plus, let's use the full derivative, df dx, right? Like that's our other, linearization that we're used to. So going from here, taking this linearization, we can take our field f, and I'm going to use capital F for our field, restricting it to C, and we get f at t naught, is approximated by, or f of t is approximated by f of t naught plus t, and plus, sorry, write this formally, df dc dc dt, right? So this thing here is something we can absolutely compute, right? Because if we take this element here and we call this bit here v, right? Then this component here, dfdc, is just tv. So the derivative of that is just v. So we have df and dc. Df dc here represents the derivative of f with regard to whatever our parameters are on f, which we'll expand a little bit more in a moment, times v is our local derivative of f at this point. And we can actually expand this further. If we look at C is a vector that's like fx, not f, sorry about this, cx, cy, cz, right? That's our space. We have df, cx, plus df, dcy, plus df, dcz, all of that on v. Shoot. This isn't quite looking quite right. And we hop back to our Mathematica for a moment while I stall for a moment, because I'm screwing up this derivation a little bit. Okay, we're back. Shoot. I really do apologize. This is not actually particularly quick to show. But basically what we actually have here is not actually a sum, right? We have the derivative of f with respect to cx. This is actually and well and truly a dot product, right? Because this derivative is actually a vector valued quantity. And for reasons I don't entirely want to go into, this is actually that derivative, df dx, df dy, df dc dot v. So we have, in other words, oh boy, where the hell? Sorry, I'm still new with this tech. Here we go, new page. So we have that df dt is equal to this partial f partial x partial f partial y partial f partial z times all of that is in, this is a dot product. You know, let me undo this and just write it as dot v. Right? So basically the idea is we look at how f depends on each of these elements, and then we look at how it applies to v. Sort of formally, we can write this without using dot product notation. We write this as df dt is equal to df dx dx dt plus df dy dy dt plus df dz dz dt. And that's just the chain rule, right? So basically we're taking the chain rule and we express it basically as this dot product of f with regards to each of its elements with respect, you know, times this velocity vector. And this basically all tells us right away what our encoding is. Because if we look at this, this sum here, I've actually sort of already arranged it into two columns. But we can actually see that there are two things. We can literally split this down the middle via that dot product. And we see that everything on the left here depends on f. This is all related to f. And then everything over here is related to our constraint c. Can you sort of see that visually, right? Cool. So intuitively, this thing on the left, this whole object, is what we're looking for, right? This object on the left combined with this object on the right gives us a way to convert f into a derivative with respect to some arbitrary constraint. And this object on the right, or sorry, on the left, is literally just called, or is not literally, this is called the gradient. This is what the gradient is. So we represent that as grad f. And there's no dot product this time, unlike with the divergence. That's because f, remember, is not a vector valued quantity. So we write grad f as this vector valued quantity. And so to be clear, f is not a vector, but now grad f is. And that's just this vector like so, except we usually write it in its transposed form. And we usually write it as the transpose because what we do is we take grad f dot v is basically the derivative of f with respect to v, where v is some arbitrary vector giving a direction. So this object here, this gradient, actually winds up being, it does a lot more for us than just tell us how to construct the derivative of f with an arbitrary constraint. It does do that, and it does that very well, but it actually becomes far more powerful. And so we're gonna take a look at that more powerful version right now once I realize how to actually stop sharing this screen and share the other screen, which I am doing now. I have demonstrated basic competence. Except I have 3 alerts that aren't going away for Zoom. Whatever. So under this approximation, we have this gradient f, which is this arbitrary directional derivative that we developed. So this gradient operator is actually a special case of something called a total derivative. And we're not going to address a total derivative, but basically a total derivative constructs a whole matrix where the matrix rows and columns contain like the derivative of the ith component of f with respect to the jth direction. And you can use that with a more complicated set of inner and outer products to extract what we need to know. But that's sort of far too complicated. So let's actually look at what the gradient looks like. So we have some function xy. And so when we take the gradient of fy, we can actually take it here with Mathematica, gradient of our function xy with respect to x and y. And it's exactly what we expect, right? So the first component, the x component of the gradient is the derivative of this thing with respect to x. It's just going to be the derivative of that term. And then the second component is the derivative with respect to y. And that's just minus 2y. And so I've actually got it plotted down here. Now, if you're kind of astute, and so you can see I'm dragging basically where the base of that arrow is, and then that arrow is the gradient at whatever point I'm on. Now you might correctly be saying, but wait a moment, Charles, the gradient's a 2D vector, and what you're plotting here is a 3D vector. And you would be entirely correct. So I'm cheating a little bit here. I'm plotting the height of this arrow, its slope, is proportional to the square of the, or not the square, sorry, the magnitude of the gradient. So that's the slope here is basically the magnitude of this vector gives us the height above the normal of this gradient. There's actually a reason I'm doing that, which will become obvious as we play with this a little bit more. First of all, we note that if we're like at exactly the origin, our gradient is 0, right? That makes sense. And as we move sort of along this surface, what we can see is that the gradient always points up the hill. Now, we sort of have this intuitive notion in our head, right, of up a hill. If you're like climbing up a mountain, that's an actual direction. There is sort of a steepest direction that is like up the hill. There's a down the hill direction, the steepest down, and then there's like side to side, right? And you could talk about that. That's something you have intuitively in your head. That up the hill direction is actually the gradient of the height of that hill. That's just up the hill. And what I'm hoping to illustrate too with this, the magnitude determining the height, is that when the magnitude determines the height, we see that it's basically always parallel to the surface. So basically, the steeper the surface, the bigger the gradient. As you can see, as I move along here, the steeper we are, the higher up that arrow is going. So the gradient actually contains a lot of information. It contains a method for finding the derivative in an arbitrary direction by taking a dot product of that direction with respect to the gradient. It includes the direction of greatest increase, which is whatever direction the gradient has, and it actually gives the magnitude of increase in that direction as well, simply by the magnitude of the gradient. So down here, we have the same plot as a contour plot, so I can do away with my little notion of like this verticality. And actually, looking at this contour plot, we see something else that's super important. Can you sort of guess what that is? Sort of looking at this contour plot, do you see something sort of really obvious? Noting that these circular rings are the contours and these arrows are the gradient. Can you notice something perhaps about how it's related? The circles are closer together, the arrows are larger. That's very true, yes. The longer these arrows, the bigger the gradient, the more closely spaced my contours are, because the quicker my function is changing. That's a very good insight. There's another insight. I actually didn't even think of that. That's very true. No, that wasn't what I was going for, but that also happens to be right and a very important insight. Yes. But there's actually something else here too. So what you said was entirely correct and actually a very useful fact. So it's not like you were wrong in any way. What I was thinking of was the fact that if we look here, the contours and the gradient are always perpendicular. Notice wherever they meet up, they're perpendicular. Wherever they like cross each other, they're perpendicular. Yeah, no, that's actually, it's a super useful fact, because what this means then is that, remember how we can like get the derivative from the dot product of our velocity and the gradient? So if they're perpendicular, that means the derivative in that direction is going to be the dot product of two perpendicular vectors is going to be 0. In other words, this gradient also encodes a little bit, sort of understanding that this gradient gives the direction arbitrary, or the derivative in arbitrary direction, tells us a little bit about how the derivative works as we rotate around through the different possible angles. It tells us if we start facing up the hill and we rotate 90 degrees, we're always on a contour. Always. There's no situation where that's not true for a continuous function. And that's kind of a very magical claim. You know, it feels like you should be able to be going, you know, in the steepest direction, turn 90 degrees and still be moving up or down. And globally, that's true, right? If we're in the steepest direction, so we're like moving up the hill here, and we move to the right, eventually we're going to start going downwards. But locally, across a very small interval, our function, remember, our approximation is basically a plane. Our approximation is planar. It's just a flat surface. And it's the tangent surface to that point. And on that tangent surface, we get this property. We get that perpendicularity, which is sort of visible here. And so now we get to sort of the properties of the gradient, which are what I was just talking about. It's always points up the hill. It's always perpendicular. It defines the magnitude and the derivative in arbitrary direction via dot product. And as you said, and I don't think I actually have it here, magnitude tells you the speed at which the function changes. That's actually, I didn't add that one. That was bad for me. I forgot about that little detail. Then we get the other really important claim, and we're going to use this a little bit later on, is that the gradient is linear. And what that means is exactly these two claims. Are you familiar with like linearity? Yeah, cool. Gradient's linear. We're happy. Then there's one other very useful claim, which, since you're familiar with linearity, I can put in a more advanced terminology, which is that the kernel of the gradient, there is a kernel to the gradient, and the kernel of the gradient is just those functions which are constant. The gradient of a constant function is 0. So we actually have a subspace of constant functions which the gradient has as its kernel. In other words, we actually don't have the curl of a function. If I just hand you the gradient of a function, if I just hand you the gradient of f, that's not enough information for you to tell me the function. You can find another function g, which will share the gradient of f. And you do that just by adding or subtracting some constant term. So in order to uniquely define a function, you need both its gradient and its value at some point p. So if you have p and f of p, you have pinned the function at one point, and you have the gradient of the function everywhere else, that's enough to uniquely define the function. And that claim is actually, we're going to build that into our new fundamental theorem. Because our new fundamental theorem is the line integral is the anti-gradient. So if we integrate the gradient of a scalar function with respect to some curve ds, which starts at a point A and ends at a point B, then f at B minus f at A is just going to be that integral. So does that, do you understand what this claim means, or do we want to go into a little bit more detail? Cool. Yeah, basically, yeah. So if you're following this, then we're good to move on. This is a hugely important claim. This is basically what lets us, do half of physics. Because it's really the generalized form, right? We've replaced the integral for the line integral and the gradient for the derivative. And in fact, we could make this a step more advanced by replacing the line integral with sort of a bigger line integral and the gradient with the total derivative, but we don't need to do that here. There's also one really important result that we'll be referring back to a few times that's sort of crucial to everything going on, which is if A equals B, in other words, if our curve ends where it begins, so our curve is closed, then the line integral over a closed curve must be 0. That's, to be clear, that's not true of any vector function, that's true of a gradient. So if I have a function and I produce a vector field by taking a function's gradient, it will necessarily have a 0 line integral around any closed curve. So this claim might sound sort of abstract, but basically what it means is that when your dad said that when he went to school, he had to go uphill both ways, he was lying, right? Because the path to and from school was a closed curve. If it went up on part of it, it had to go back down on the other part so that it would come out to 0 again. I know I'm over-explaining the joke, but I actually think that's a pretty good way of understanding why this closed loop integral has to be 0. It basically comes from the fact that the function is well-defined. In order for our thing to return to its original value, that closed loop better come out to 0. Otherwise, you could walk in a circle and wind up higher or lower than where you started. So the gradient, as I said, we take a scalar function and it produces a vector function. So you might remember from last time that a divergence takes a vector function and returns a scalar function. So that should give rise to an interesting question. 2 of them, actually. So what does it mean to be the gradient of a a gradient of a divergence? And what does it mean to be a divergence of a gradient? So the divergence of the gradient of a function is called the Laplacian of the function. And it's beautiful. The Laplacian, you're going to use it a lot. We start getting into ideas of like harmonic functions. You're going to use it a whole bunch if you ever do things with like diffusion, if you ever do things with complex functions, complex analysis, you're going to be using a lot of Laplacians. But for now, we don't have to really worry about it, aside from saying it is a certain quantity. And then the other question, what's the gradient of the divergence of a vector field? There's no fancy name for it. It's not anything you need to care about. So basically, the conclusion here is right now, we're really only going to concern ourselves with the gradient, because we actually wind up not being all that interested in, basically, you can sort of think about these, if the gradient is sort of an upgraded form of the first derivative, these are sort of the upgraded forms of like higher derivatives. So now we're going to sort of talk a little bit about, basically up until this point, everything I've been saying has been very mathematical. You've heard me use physical systems as an example, right? You've heard me talk about like height, height, acceleration, velocity, all of these things that are physical, but only because they're useful mathematical examples. But let's actually go and say, tomorrow I'm going to be giving you a problem set how does this help you with that problem set? How does this actually make your life easier? Because if I'm going to talk to you for an hour about pointless claims about derivatives, I think I should at least be helping you with tomorrow's problem set a little bit. So we actually do this by remembering that the work is known to be, so work in physics is the change in energy. And this is a delta, it's not a Laplacian, it's a delta. And the work can be described as the integral of the force times the velocity over some time t, right? So the work done to an object is the force times the velocity over some time t, and I'm using s here to represent the total curve, but really we're restricting it to a curve with parameter t, right? So we have some position curve. This is the position curve's derivative with respect to t, and we're doing it over the time. And then so we take the dot product of the force with the velocity over the path, and that's work, right? You learned that in the last physics course, I assume? Cool, yeah. So we can therefore obviously say that dE is f dot v ds. This is, I mean, you've done this, right? You probably used this to solve problems before, like what's the kinetic energy, yada, yada, yada. Boring as hell, but fundamental physics. But if we imagine the energy function as a property of position, so we create an energy field, which sounds like something out of Star Trek, but I mean, it really isn't, right? Because we have these ideas of energy fields, like voltage or gravity, or gravitational potential, I should say, right? Some places are just higher energy than other places. Rocks on top of hills are more dangerous than rocks at the bottom of hills because they end up going faster when you kick them. Really basic claim. But that's the analogous to thinking of energy as a property of position or a function of position. Then we can write the energy at some position B minus the energy at some position A plus like a kinetic energy change is this dot product, is this change in energy. So what we're saying here is we imagine that our particle has inherent in it some energy depending on where it is. And that energy, depending on where our object is expressible as a function of space that says, if our object's here, it has X joules. If our object is over there, it's got Y joules. And then there's also like this kinetic energy term, right, VF. And we can basically say that the change in our potential energy plus the change in our kinetic energy, that's going to be the total change in energy. And so it's going to be this line integral. And we're saying A and B now are the terminal points of some curve S. Now we make a further assumption, which is when we're moving our particle through this curve in space, we do so in a way such that our velocity may change over time, but its magnitude will be held constant. So I'm actually going to go back to the iPad here, and I'm going to do the next bit on the whiteboard. So there we go. I need to clear chat. So basically what I'm saying is that I have some parametric curve S such that my velocity along this curve, it has the property that this is some constant C. Then what we have is that along this curve, if this is A and this is B, we have E at B minus E at A is equal to that integral f dot v ds dt. We'll say ds from A to B. So next, our question is, so what is f? Well, let's say f is composed of two components, right? If we take, it's going to have some component fv, in the v direction. I shouldn't be using dot product there. FV plus some perpendicular component F perpendicular, not V, F perpendicular, we're going to call this vector here P as our perpendicular vector. Or actually even better, let's call it N. So that's normal to V. So our basis right now is V and N. Well, let's look at these terms. Since the velocity, the net velocity is constant, this term here has to be F net dot V is equal to 0. But if F net is equal to like some pushing F plus some other F from, we're going to call this U, some F due to a potential field. So that's like gravity, or that's like some external force that we're using for this problem that we want to develop on. And we're gonna see exactly what this little U term winds up being. Then we have, let me actually go back to that slide. F applied dot V is equal to 0, right? So if we want to look at this term, we say that like F applied dot V is equal to minus FU dot V, right? So that their sum comes out to be 0. And now when we integrate F dot V, we get the integral of F applied dot V is what we're looking at, right? Because we're concerned with the work done by our applied force, right? So we can actually rewrite this as minus FU. So we can say that our applied force is the negative of our U force dot V, and we're actually not too concerned about the perpendicular force, because that's not going to contribute to our final energy. So all that's going to do, we see, is that we can write EB minus EA is equal to that integral of F applied, which is equal to minus the integral of FU dot V ds. And can you tell me what that looks like? Hint, it's what we've been talking about all day. Yes, that is the formula for energy, but I mean mathematically. What does this look like mathematically? Think in terms of what we were just doing. That's fine, that's fine. What this is looking like is basically what we get here is that F minus F, rather, minus FU is equal to grad E. Like if we compare this equation here to our equation for the gradient, which we remember is that like some function at B minus some function at A is equal to the integral ds of grad F, then that's the same equation, right? It's just that grad F here is FU, or minus FU, and then this is our energy term. Kind of drew this terribly. Yeah. It's a little bit confusing because in one case, F is the force, one case, F is being used for function. I fully admit that my notation was kind of terrible. So if we stop sharing screens, we go back to Mathematica. This is sort of the punchline. This is why you should care. And this is what matters, is that the gradient of the potential energy is the negative of the force due to that potential energy. And this is true basically for any position-dependent force field. Any old position-dependent force field can be used to produce a potential energy term. So we can actually say that if, remember that the voltage is defined as the potential energy per unit charge, and the electric field is the force per unit charge, then we could actually go a step further. Instead of saying the electric potential comes from the electric force, we can actually say that the voltage comes from the electric field. And again, we're using E a bunch for like different things. This claim here is that the voltage is the negative of, or the gradient of the voltage is the negative of the electric field, or sometimes you see it written the other way. Does that make sense? And it's important to highlight, this is not a special property of like voltage and electricity. This is not like a special, we never used Coulomb's law in here. We never made reference to any old properties of electricity about like electrostatic force. The only thing we were referencing in doing this derivation was simply that there was an electric force and it depended on position. That's all we did. We said there was some electric force field that was position dependent. And then we said, all right, we treat it as a gradient. We write out like the energy at two positions. We simply made the assumption that our energy could be given as a function of position. And then we showed that if we make that assumption, then it pops out clear as day that force winds up being what you need, that the negative of the force gives you the gradient of that potential. And we chose to divide by Q. We chose to look at how it was related to charge, and we got out this relationship between the voltage and the electric field. This also gives you something. For example, this tells you that there should be a potential field for gravity, right? Gravity is a force. It points in some direction depending on your position, with some intensity dependent on your position. This tells you that there's an equivalent to quote unquote a voltage field that's the electric or the gravitational potential field for mass. And I mean, in class, you've seen that, right? You've seen that like E gravity is equal to mgh. Well, that's a vector field, right? Because h is just z. That's a vector field. And that's just telling you that the gravitational potential has as its gradient, or the gravitational potential is just a linear function of height. So its gradient, what's the gradient of something that has only a z component? Its gradient is going to be the up z direction. So the negative of that gradient is going to be downwards in the z direction. What's that? What always points downwards? I mean, that's just gravity. That's gravitational force. Clear as day. But this actually brings up a very important question, right? Because now we've got this idea of this force energy equivalence going on. So can all vector fields be written as the gradient of a scalar field? If not, what properties are required to make such a description possible? And I did say take a few minutes to consider that question among yourselves, but there's one of you. So what do you think, Jackson? Do you think we could do this for any force? Good, you've got the right intuition that we couldn't do this for any force or any vector field. And actually, the objection is exactly this claim we had right at the beginning, or not at the beginning, earlier. The claim that the loop integral of a gradient must be 0. You could imagine a vector field that's swirly, and that's a highly technical piece of terminology. I only use the most technical terms. But like, if we defined some function like that, then we do vector plot counterexample y, something like that. I mean, it's pretty clear if you're looking at this that the closed loop integral here is not necessarily going to be 0. So we couldn't, for example, define a potential at some point here and another potential over here, because it would matter if you went that way, or like if you went the other way, it would be negative, but if you went that way, it would be positive. And like all of a sudden, like you can't do this. So the claim is that the closed loop integral must be 0 no matter what loop you choose, no matter how you construct your closed loop. As long as the integral over that loop is 0 for a vector field, you can write it as the gradient of some scalar field. In fact, you can write it as the gradient of infinitely many scalar fields, remember, because we have that constant term. We have that kernel, which is non-zero. So when we get to curl, what we will learn is that the curl being 0 is the property we're looking for. But for now, we can think about this. There's two terms for it. One is that it's a conservative vector field. And that's not talking about its opinion on abortion. That's talking about whether or not the vector field here it sort of conserves the dot product. Like if you take a loop around it, is it going to come back to the same thing? Another way of referring to that is it has to be path independent. If I have a line integral from point A to point B, if we go up here, like if I do a curve up to here, like along some path, or like a curve along a different path, those line integrals have to be the same if they start and end at the same point. In other words, when I'm doing this calculation, this calculation of the integral of my gradient, it didn't matter what path I chose. All it mattered was B and A, right? Like this right-hand side, there was no like reference to some intermediate point C, no dependence on like how long it took me to get there. All it mattered was where I started and where I ended. So those are all equivalent statements, and those are all the requirement. And so that requirement exists in electrostatics, that the curl of the electric field is 0. When you get to the M part of E&M and get to magnetism, we're going to start running into cases where that gets wonky, where that stops being true. But in electrostatics, we have an electrostatic potential. We know that the curl is 0. If you're ever asked to take like a path integral and you're looking at that path integral for like the the electric field, and you're like, I don't want to take the integral over that path, just choose a different one. Take the line integral of the electric field over like a totally different path. As long as you start and end at the same place, you'll get the same answer. This is a very useful tool for making your life easier. Maybe you've got some really wonky line integral, you have no idea how to do it, but there would be a really easy line integral that gets you to the same place. Just do the easier one. You're going to get the same answer. You're going to get the same answer because the electric field is the gradient of the voltage. Now you're probably, so I've shown you like this argument here, right, that says the gradient of the voltage, I should probably, is the electric field, or the negative of the gradient of the voltage. And that negative is basically because the force pushes in the direction of lower energy, right? Gravity pushes down, not up. And that's why there's that minus sign. It's because balls tend to roll down the hill. You never really hear about like something falling up the hill, falls down the hill, falls down the cliff. So cheating a little, or not cheating, you're sort of looking ahead. Let me put my money where my mouth is and actually show you how we compute what the voltage is. For the simplest case, and the simplest case is we have some point charge of some charge Q. Then we have some position R, distant from Q. We're going to orient our coordinate axes so that Q is at the origin. And I want to know, what is the voltage field due to Q? How does Q produce a voltage field? Well, we're going to start with the equation for E, right? So E is R hat Q over 4 pi epsilon naught R squared. So that's our electric field. And we know that's equal to minus grad of V. So we go on to a new slide, and we can say V at R minus V at some point P, and we'll choose P in a moment, is equal to the integral of minus E from P to R ds across some path, right? So if we have our charge here, Q, we have some point R, we have some point P, we can find what the difference in the voltage is. And the fact that we only find the difference is kind of important. Now, it might be intuitive. We're going to look for what do we choose for P? Now, the obvious choice would be, let's just choose the point Q, right? Let's say P equals 0. And that seems like it would be a good choice, sort of intuitively. But can you see what the problem is with choosing that point? I should mark this as like R hat. Well, remember that we're going to be looking at like this integral. So what is E near Q? Well, the top term Q is fine. The lower term, 4 pi epsilon naught, and we have this R squared, right? So what's wrong with this R squared? Well, R squared goes to 0, right? Near Q, this is about 0. Right, that length gets shorter and shorter. So this here would actually diverge. This integral wouldn't work. We can't actually find the potential at that point charge Q. And this sort of makes sense, right? As you get closer and closer, let's say I'm carrying a small positive charge as I approach Q, the force is going to increase and increase infinitely. No matter how much I push on my point charge, I'm never going to be able to get it to overlap with another point charge because the force will always eventually exceed whatever force I want to put in. I will never be able to align them. So actually asking what the potential is at Q doesn't really make sense. It actually doesn't make a whole lot of sense. So now we actually, let's look sort of a little bit harder for where we want to put P, or our point P. And I'm actually going to tell you that the most intuitive position is actually to go the other way. What if we said P was very far away? Highly technical terminology, as you can see here. So we have like our point Q, and we have like R. And then what if we just went really far away, further than you're thinking, however far you're thinking, further than that. And then we chose P. In other words, P is actually infinity. We're actually going to go infinitely far away. Now, obviously, going infinitely far away is a little bit ill-defined. As physicists, what we're saying when we do this is P is just really far away. It's effectively infinite. It's so far away that we stop caring, right? If my charge is a nanocoulomb and I put it here in California and I go back to my undergraduate college in Philadelphia, I can probably just forget about that little point charge, right? Like that point charge isn't going to matter. I'm basically infinitely far away at that point. Now, as mathematicians, we might object to that. We might say, well, but that's not infinity, right? That's not quite infinity. So actually, really secretly, we're taking a limit as P goes further and further away. Mathematically, that's what we're doing, but we're physicists. Remember when I said this was a glitched speed run? Some of the glitches include things like going infinitely far away from an object and still being within our space. So now we have our integral. V at R minus V at P is equal to the integral from infinity to P, to R of Q R hat, or I should say negative Q, because remember we have to take the negative of E, over 4 pi epsilon naught R squared d ds, change in position. So this integral might look hard to resolve because there's this little infinity on the bottom half, but this integral is actually entirely doable, right? So what's the integral, what's the indefinite integral of this thing with respect to R? So basically what we're doing is we're linearizing this, first of all. So we have our Q, we have R, and then we're going infinitely far away, like in the same direction. So we're not going to worry about taking some like sinusoidal path. That's not going to happen. We're just going to take the linear path towards Q, starting from infinitely far away and ending at R. So that makes this integral one-dimensional, so that we can really, R here really is a scalar. This R is a scalar, this R is a scalar, this infinity is a scalar. God, that hurts to say. As a mathematician, saying infinity is a scalar, it pains me. But basically, we're taking the one-dimensionalization of this problem. So what's the integral of 1 over R squared? What's the indefinite integral of Q R hat ds over 4 pi R squared epsilon naught? And we can replace this ds dot dr dot R hat. We can actually say that's going to be, well, ds is going to be inwards, R hat is going to be outwards, so that's going to be another negative sign, so those just cancel, and we're left with dr. What's this indefinite integral? I don't know how much calculus you remember, but that's just going to be minus q, because remember those first two minuses canceled, but we got another one, 4 pi R squared epsilon naught is equal to the indefinite integral. So going on, what does that mean for our voltage at R? Our voltage at R minus our voltage at infinity is going to be Q 4 pi epsilon naught R, over R, minus Q over 4 pi epsilon naught at infinity. So what's this term? What happens when you divide by infinity? Yeah, so we can actually just kill that term, get rid of it. It's gone. And we're left with this expression. Equals VR minus V infinity. Then we're left with one final question. So what's V infinity? Well, remember when we said that our gradient only could give us like the change, right? We can say V our vector is equal to like V plus any C, and we get the same E. So what does that mean? It means here that basically V infinity can be anything. We can choose any value. Now, the most common choice is V infinity is equal to 0. There's a few reasons why we might set V infinity equal to 0. The most intuitive argument is probably if I'm infinitely far away from my charge, nothing's happening. I shouldn't have any energy due to my relationship with a charge that isn't actually acting on me, right? If there's no force on me due to that charge because I'm so far away that that force doesn't matter, that shouldn't affect my energy. The answer shouldn't be like 3, right? Because then if I add a bunch of charges over there, does that mean my new potential is like 6? But nothing's changed for me. If you add more charges over there, nothing changes for me. So why should my value be anything but 0? You know, if I increase Q, certainly it shouldn't matter. Like 0 just sort of makes intuitive sense. But that's not always the choice we make. And I'm going to stop sharing screen now. Because now what we have is we have our voltage field. How do I stop sharing screen? Sorry, I'm still new on this iPad. There we go. This will be more polished later. That's a lie. Well, there are other options, and I actually talk about it down here, which we'll come back to what I'm talking about with gauge theory later, and say V0 is at infinity. But the other solution would be to ground something, right? Like if you're doing electrical engineering, we say that the Earth has 0 voltage. And there's no magical reason for that, right? We could imagine that actually the Earth is near some really strong voltage source somewhere out, you know, in Alpha Centauri. Maybe there's something with a lot of positive coulombs. Maybe the Earth actually has a positive voltage. But we can choose for it to be 0 because, well, we get to choose. We get to set the voltage equal to 0 at some point in our system. We get to choose basically wherever we'd like. We could say that the voltage is actually 0 at some specified radius capital R, and then we'd be taking like the voltage is this minus the voltage at capital R, so it'd be that minus Q over 4 pi capital R epsilon. Does that make sense? Yeah, cool. Now, remember the principle of superposition for the electric field, right? That just says if you have 2 point charges or some distribution of point charges, the total electric field is just the sum of the electric field due to charge 1 with the other the sum of the electric field with charge 1 with respect to charge and the field due to charge 2, right? Superposition. Now, we remember that our linearity constraint says that the sum of 2 gradients is the gradient of the sum. So if the sum of 2 electric fields is a new total electric field, then the sum of their antigradients, so the sum of their voltage fields, should be the sum of their voltage fields should be the voltage field of their combined charge. Does that make sense? So if I put 2 charges next to each other and I want to find the voltage at any point, I find it relative to the first charge and I find it relative to the other charge and I add them up. We can actually stop assuming that our charges are local. We can actually go away from the idea of charges at points to a charge distribution, like you've seen in class before. And we can make this claim. The voltage due to some charge distribution rho at some position x naught is the integral across all of space of rho at that point times this. And what this is just this with R, remember, is the magnitude of the distance between our points. Actually, the magnitude between x naught and x, so the magnitude of the vector from x to x naught, times rho of x, so the charge distribution of x, and if we integrate that across all of space, so across all of the charge distribution, that is the total voltage field. And does that follow? Excellent. So this leads to a pretty obvious claim, and I hope it feels obvious. If you know the charge distribution rho, and we set the requirement that V infinity be 0, that's sufficient to define the voltage everywhere in a system. If you know rho, and you know that V infinity is 0, you have this formula, you can find the voltage everywhere. And of course, that also gives you the electric field everywhere. That's easier said than done. Actually, computing this integral, I'm getting a PhD, and I'm learning how to compute this integral in special cases, basically. But there's something valuable to note about this expression. And this notice is something very mathematical. This is actually a convolution. So we have convolved this function, v of r is that, with rho of r. Have you seen convolutions in mathematics before? You may have encountered them in statistics. That's not actually that surprising. Convolutions are a tool that's very powerful, but can be very hard to sort of visualize. But what a convolution is, and it's usually written using the multiplication asterisk, so kind of like v times p. That's actually not times, that's convolved with. So v convolved with rho. It's this expression here. This is the expression. And so the way to think about that, yeah, you haven't taken statistics? Yeah, it's used a lot in statistics. It's actually used in harmonic analysis, which is a branch of mathematics that physics relies on, but is a little bit more advanced than what you'd expect to see at the undergraduate level, unless you're a maths major, or maybe a maths minor. I don't actually know how UCI does things, so maybe you'll never see it in undergraduate. But we can think about convolution as like we imagine our functions v and p, and we sort of like imagine drawing them out. And we imagine like taking the point x naught. So we take some point and we move, and this is going to sort of be wishy-washy. We basically move v around x naught and rho around x naught in opposite directions, right? So we see that rho of x here means subtracting the same quantity from v. So if we have our point x naught, v of x naught, and then we move v minus x away from x naught, and we look at p plus x away from the origin. And we do that for all possible choices of x, and that's what a convolution is. Yeah, right? There's sort of a symmetry going on here. In fact, we could switch which of v and p we were actually convolving. We could swap their orders and we get something similar. It's sort of like, you know, it's like moving around a mirror, right? Like as you move away from the mirror, your mirror self like moves into the mirror. It's the same thing around like this point x naught. We move v away, and you know, in some direction, we move rho away from the origin in the opposite direction. And we use this tool in a few different ways. One way to use it is to combine a distribution and the effect of that distribution. So like we have some effect that's caused by point charge. And then we have a bunch of different point charges in different places, and we combine that into the net effect. We often do that with convolution. That's what happened here. We can also use this to compare functions. There's something to be said that the convolution of like a function and another function at x naught sort of tells you how similar those functions are up to being moved around a bit. And we're not going to sort of look into what that means, but my undergraduate thesis made heavy use of convolution. And it's important to note here, so rho of x, I said rho of x was a function, right? Because it's the charge distribution. But rho of x is, more strictly speaking, it's a distribution. And you might be wondering, well, what's the difference between a function and a distribution? Well, it's that rho of x can contain the idea of what's called point mass. So in this case, what is rho of x for a point charge, for simply a point in space? It's not just like 1 at that point in space, because then the total integral would be 0. Right? If rho of x was just a regular old function, you couldn't have a point charge. Like we've been studying point charges, we place a charge at a point and do something. Well, that's not possible if charge distribution is merely a function. Somehow we want this idea of charge can be spread out over a space, or we can cram it down into a single point. And this idea of cramming something down into a single point is the difference between a distribution and a function. And this is, again, very much like I'm sort of talking about this in the sense of a physicist. And the real difference, and we're going to look at this in our example, is the Dirac delta distribution. They call it the Dirac delta function, but it's really a distribution. And the Dirac delta function has the property of being 0 everywhere except the origin. So the Dirac delta function at x is not 0 is 0. Yet the integral of the Dirac delta over the origin. So if you take any integral of the Dirac delta which contains the origin, the integral is 1. Which intuitively is impossible, right? That's not possible for a function. If the function has 0 width, it can't have non-zero area. And that's why the Dirac delta is not really a function, it's a distribution. And rho of x is actually allowed to have this distributive nature rather than this functional nature. So rho of x can contain these Dirac deltas. We're actually going to look at an example of that here. And basically, we can think of this Dirac delta as reducing sort of the dimension that our distribution is over. So this is a charged shell. So we have rho is a distribution over radius and 2 angles in spherical coordinates. And we say it's the Dirac delta of the radius minus some number a greater than 0. So that's basically saying the charge is 0 everywhere except on a spherical shell of radius r. But there is still charge. The charge isn't 0. So that rho means, the Dirac delta means that rho is distributed over that 2-dimensional surface instead of the 3D space. We could actually put in another Dirac delta with respect to like theta, and now it would be distributed over a 1-dimensional surface. It would be a line, or a curve rather, on the surface of our sphere. And if we put in a third one with respect to phi, now we'd be uniquely defining a single point, and we'd be putting all the charge in a point. So that's what Dirac deltas are. So that's what we see here. If a is greater than 0, what's the charge at 0? Well, it's 0. What's it at any point other than a? Like if we say like, it's always 0. Right? But then if we integrate, and let's say a equals 1, just for our convenience. So what's the integral of this Dirac delta throughout all space? Well, it's 4 pi. And it's 4 pi because we're integrating this Dirac delta, which is that spherical shell, over the area of that spherical shell. So this reduces the distribution to be of density 1 over an area, and then we actually get what is the area of a sphere? It's 4 pi. Well, it's 4 pi r squared, but it's 4 pi when r equals 1. So let's do this convolution. And this term here, this is just the spherical area element. It changes dv into dr, d theta, d phi. Well, let's integrate this and get 1 over epsilon. What are we doing this time? So we're doing this integral, right? This r here is basically this is the magnitude. R here is x naught minus x. So if that's just r is the distance from the origin. I'm asking what's the voltage at the origin? 1 over epsilon. And that's what you'd hopefully expect if you've seen this before. Well, let's ask, and this is really ugly. As you can see, taking this integral, this convolution is not always easy. Fortunately, I have computers to do things for me. What's it 0.5 units above the origin? So this, I assure you, is the formula that says the distance from 0.5 units above the origin to any other point. I promise you. It may not look like it, but it really is. Well, what's the integral at z equals 0.5? It's also 1 over epsilon. Well, what's the integral at any position on the z-axis less than 1 unit away from the origin? 1 over epsilon. So if I have a spherical shell with some charge q on it, the voltage inside that shell is constant. You've learned that before, right? The voltage, the electric field inside a spherical shell with charge on it is 0. The electric field inside that shell is 0. And we know that because of Gauss's law, right? You've seen that before? Yeah. And so because the voltage is exactly 0, or sorry, the electric field is exactly 0, the voltage must be constant, 1 over epsilon. Well, let's move outside now. Let's look at like a distance of 2. So now we're outside the shell. Well, then it's 1 over 2 epsilon. What about at 4? It's 1 over 4 epsilon. And in general, it's 1 over r epsilon. So we remember that q is equal to 4 pi, and we go up and look at our formula. If q equals 4 pi, it cancels. That's the same thing as if we had a point charge at the origin. And you probably learned that as well, right? Outside a spherical shell behaves like a point charge in its center. And that's purely visible from this process of convolution. I mean, I suppose it's not particularly visible. It's actually incredibly opaque. I would have no idea how to take this integral had Mathematica not done it for me. And you might say, well, Charles, that's all well and good if we're on the z-axis. But you enforced that our position was on the z-axis. You only moved up and down in z. You never talked at all about what happened if you like move a little bit on the x-axis. Well, that's symmetry, right? A sphere is symmetric. All directions are the same. My answer worked for the z-axis. But if I just rotate my system so that the z-axis is now like along the x-axis, along the y-axis, or in any other direction, nothing changes. So this solution is actually universal. This tells me what it is at any distance r. And that gets us, again, this voltage field. We can plot this. How do I do this again? That's f, yeah. Let's normalize epsilon. Epsilon equals 1. This is let's say like 100. one moment. Need to do, nope, still doesn't like it. Let's not do 100. There we go. Right, so this is our voltage field. Inside the sphere, it's constant. Outside, it goes away. Could even do this as a plot, 3D, from obviously I can't do this for like an actual sphere, like in all directions, because then you couldn't see the voltage field, right? That would need to be 4-dimensional. But let's do this for the other case. And we can see what we get, right? A little popped out internal segment. Now, this should be continuous. I'm not really sure why it isn't. The surfaces should touch. I think it's just because the piecewise is having a little bit of trouble. The piecewise plot isn't working perfectly. But like that's the voltage sphere, voltage due to a, well, it's a sphere, but of course we're only looking in the X and Y directions. Isn't that neat? Well, that's all just due to this convolution method. And actually, you've been such a good audience, such a good audience of one. Let's give a little bit of a teaser towards something a little bit more interesting. Remember we were talking about the V at infinity is 0? Well, we can choose wherever. There's actually even more freedom in our choice of C. Since we've been doing electrostatics, we never ever used the word time, except maybe as the parameter for a curve. In fact, our definition of the electric field as a function of the voltage field, the voltage field as a function of the electric field, that all has to do with space, no time terms. That means if we rewrite C as some time varying constant, so C varies with time, that doesn't do anything to our electric field. Our voltage field can be time dependent, and yet our electric field can remain unchanged. So long, what that means is basically I can choose a different 0 voltage now, and like 2 days later I could say, I changed my mind. 0 voltage is no longer at infinity. It's actually the surface of the Earth. Wait, no, I changed it again. It's actually my right hand. My right hand is at 0 voltage. The universe is defined around that. No, actually, I changed my mind. The 0 voltage is actually defined 1 millimeter away from this giant electrostatic capacitor I have. I could do that. And that wouldn't change anything. We could choose any old function. It doesn't even need to be continuous. Now, as it happens, when we introduce magnetism, and we're going to do that, in this class a while later, that actually starts putting a restriction on our C of t. And that restriction shows up because the magnetic field interacts with the electric field in certain ways. And really, they're both, and you're not going to learn this until maybe your senior year at most, but like they're both actually functions of something called the A field or the vector potential field. So the voltage is actually itself function of something called a vector potential that isn't a scalar, and then the magnetic field comes from that same vector potential. All of that puts constraints on our choice of C and C of t. And I will assert to you without proof, argument, or reason, brokering no question, no compromise, and no substitute, that if we actually looked at this at a really detailed and advanced level, and that's called gauge theory, with C of t being a gauge field, that would tell you why electrons have charge. It's why photons exist. It's why light exists. It would actually prove that there are 8 gluons, which there are, and it would tell us why the Higgs boson was predicted. The reason we knew there was a Higgs boson was in large part due to doing this, looking for these extraneous degrees of freedom in these potential fields, basically. I mean, far more advanced than that, different types of fields, different types of degrees of freedom, the same idea. And And if you really want to get into gauge theory, I encourage you to pursue a PhD in theoretical physics. Then we can be friends. It's fun. We can actually be friends. You will graduate from college before I'm done with my PhD. And if I can get 3 more people to sign up to my pyramid scheme, sorry, I mean to academia, I go up a level in the whole pyramid and I become an assistant professor instead of a TA. They don't tell you, but that's how it actually works. You just got to sign up people under you. It's multi-level marketing. It's a pyramid scheme. But that's all for today. So do you have any questions? And would you rather I stop the record? If you do have questions, would you rather I stop the recording before talking? Cool. No questions, then I'm going to stop.